Okay. First we are looking at the and or gate. Means like as you see for and, when both are 1, then only it results in 1 and otherwise 0. While for or gate, it results in 1 for all the cases that has at least 1. There is there is a 1. It will result in 1 in that case. Uh, just to wait a minute. Okay, while it is going on. Uh, so, we use a perceptron here, that is a a neuron, means, or to say like there are x1 and x2 as input, okay, and 1 is the bias term. They have their respective weights, okay, and okay, and they have their respective weights, theta 0, theta 2, theta 1, theta 2. We apply and to form a linear combination of the form theta 0, theta 1, and means theta 1 x1 plus theta 2 x2, right? And so then after that we apply a non-linearity, because we need to classify, that is, in such a way that when the combination value is close to 0, means it is when the combination value is negative, means less than 0, it results in 0, otherwise it results 1. Okay, usually we use non-linearity sigmoid. Okay, okay, so this is the idea. So that is how we form classifier. It is called the perceptron. After that, uh, and in this diagram I have formed the, okay, let's clean this up, okay, confusing. In this diagram I have formed the uh, or, okay, and this is the classifier. Okay, so what I have taken it as the middle point, okay, somewhat in the middle. Okay, so one such or classifier is this one. That is an example. There can be several more, okay, from here till here, or at different angles as well. Okay, it is at 45-degree angle, so this is one of the or classifier. Okay, and if okay, so if these three are zeros, okay, as you see in the AND case, and this is 1, then this can be the classifier for the AND. Okay, this is just an example. Okay, means like I have drawn this example in such a way that means I have deduced this example, like this is 0 comma 1. Okay, so I am thinking of a 45-degree line, means like 135-degree. Okay, this is 135. Okay, so in that I am looking for exactly half. intercept. Okay, so this has to be 0.5, right? Okay, so this coefficient has to be 2. Both of these has to be 2 because 45 degree. Okay, so that is how I've come with this classifier. And in case of uh, this one, suppose it is um, and then it has to be more than 1. Okay, so 1.5. So that is how I've come up with the classifier. There can be several more at different angles, different intercept. Okay, so this is the AND or gate classifier. Uh, this case is called the linearly separable one, as you can see that with a let me write it down, with a linear decision boundary. Linear in the sense that this, first of all, this is a linear combination, and second, the power of x1 and x2 is 1. Okay, so this is a like a linear, okay, linear combination, linear, if equate to 0 then it's called linear equation. Okay, so that is why it is called linearly separable. Means with a straight line I'm able to separate the two data and able to classify. Okay, but here is our case of XOR, that is if 0 0 then 0, 1 0 then 1, 0 1 then 1, 1 1 then 0. So this is the form for XOR XOR case. So as you can see, it is clearly not separable by one line. Okay, so the idea is that now you have to use more than one perceptron interacting with each other. That is what I mean. And that is I mean that means one perceptron taking the input from another, means output of another as input, and somehow means able to classify this one. Okay, so that is how we came to the idea of neural networks. So the data which is not, means cannot be classified linearly, we need to use when the data is not possible to classify linearly, we need to use more than one perceptron in unison. Okay, so so there is nothing extraordinary, it is just a network of neurons. Okay, okay, so as we most of the cases don't know how to structure this network. Okay, so uh, we add and connect all of this neuron every way possible. Okay, so these are also called neurons. Okay, inspired from the biology term neuron. Okay, and so suppose this is the input layer, like 1 and x1 and x2. Okay, and
Excuse me, sir.
hello.
Sorry to disturb. In yesterday's class, already this is covered, so better you solve the other problems which are there in the assignment, similar types.
uh, yes, so the
So
problem,
already Baban Gain sir has covered yesterday. This is already. So please solve the other problems, sir, which are there in the similar type assignment.
yes, let me search first of all. Google. NPTL, right? Let's get to the problem. This is the one. This is the one. Okay. And week 5. Right. And okay. So, so the first question is about the structure of a neural network. Okay. That was I was just going to explain. Okay. So, so maybe there are some internal nodes, internal neurons in the inner layer, hidden layer, and there is neurons on the outer layer. And means I'm talking about the question number one, an input layer. Okay, so I was going to do the same thing. Okay, so sorry, here is the diagram to explain that. Okay, uh, so so this first layer, that is the input variables, and the bias term one here. Okay, is called the means input layer. Okay, and the this inside two layers are called the hidden layers. Okay, and the last layer is called the output layer. Okay, and I have taken this slide from Andrew Ng's course. Okay, so uh, let's go to this problem and see that you have to estimate how many parameters to train here. Okay, so first let me explain how does it work here. So mm, so okay, so first of all we connect means to every neuron to every other. Okay, so to calculate this value, and okay, okay, so what we do here is that uh, let me explain carefully. Okay, so in this example they have taken one here. Okay, 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 so we call this as layer 1. Okay, this is layer 2 and this is layer 3. Okay, and now the uh, the value at this point is like denoted by x. Okay, of layer 2. Okay, this is the notation here. Okay, x of layer 2, and this is the first value, is first neuron in this layer. So 1, okay, and 2. So this is x of layer 2 and the first neuron in that layer. Okay, and and with respect to this, okay, to calculate this x1 2, okay, so that is the neuron of second layer and first element. Okay, value at this stage. So also there are the bias term here as well. Okay, is a 1. Okay, and here like that. Okay, so what we do here is that first there is the non-linearity g here. okay, also called activation, okay. And what we do is that for calculating this, we need to take account of these three, x1, x1, and x2, okay. So that is going to be theta of layer 2, okay. For layer 2 we are calculating, okay, 2 2, okay. From like x2 1 comes the theta 2, okay. And the corresponding we're going to the layer one's first element, or maybe zeroth element, because it is the bias term, right? Like that, okay. Multiplied 1, okay. Then theta 2 and layer one's first element, okay, into x1 plus theta 2 and first layer second element multiplied x2. So this is how we calculate x2, okay. And this theta 2 1 0, theta 2 1 1, theta 2 1 2, these are the parameters, okay. That is that we have to calculate in this question. Means how many such parameters will be there, okay. So like x2 1 I have calculated, okay. And this linear means this linear combination is usually denoted by z21, okay. Z means it is called z usually, okay. Then when we apply this non-linearity or activation, we get the value of the neuron, output of the neuron at this level is called output, okay. What this neuron will output here, okay. Similarly we can calculate x2 2, okay. So let me clear it out a little bit, maybe use another slide here, okay. So that is how they have calculated here. Means like this for Andrew and G's course, okay. So I have used x21 here, so they have used a in place of that, okay. Otherwise same, okay. So means for every connection there will be a parameter theta here, okay. So the question is to find how many such thetas will be there. uh, just let me give another example to make it more clear. So okay, so we have calculated this x21 here. We can also calculate x22 here, okay. That is going to be x22 is equals to g of z22, okay. And z22 is going to be theta 0, means for layer 2 and from 1 to 0, okay, of layer 1, and maybe the connection is written. What is the notation here? So it is like that, okay. You get an idea. We are calculating the weights, okay, means calculating the output at every neuron layer, okay, till we get the final output, okay. So Uh, so this process is called the forward propagation. Okay, and well, let's solve the question now. So we're ready to solve now. Maybe new slide will be better. So if you see, the question is like, uh, so any doubt in this question, means like, have you solved? Anyone has solved? Acha, many people wants to join. Okay. So somebody has solved this question. What will be the answer if somebody has done that? Hello. Anybody has solved this question? This is actually a very good
Yeah,
question.
yeah. Option C.
Option C or A, B, C. No, actually, not option C. Okay, let me explain actually. Okay, answer. Okay, let me not say the answer. Maybe you can work on that more. Let me explain. Answer is not C actually. Let me explain how it. Okay. Uh, some message. How should I admit? Okay. So some theoretical introduction was needed before we can progress into the question. That is why I was explaining. After that, it gets very easy. So what they have said is like, uh, that there is a p-dimensional input. So in our example, there was two dimension, x1 and x2. So two dimensions, okay. But they have like a p-dimensional one, okay. Suppose four. For the matter, say four. That is our four-dimensional input, okay. And 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 the bias term will be there also. Actually, ignore the bias. They have written, okay. Simplifies the process overall. So overall, you can ignore it. That's no problem. So okay, and they have said that there are uh, m hidden layers. Okay, so like there are like m layers here. Okay, suppose in each layer they have written that there are k hidden units. Okay, but suppose the number of input dimension is 4. Number hidden input output hidden layers means like number of units in hidden layers is 5, let's say, for example. Does not have to be, but just to take an example. Okay, and like so these are k, number is k here, this is p. Okay, such m layers here, m such layers, okay, which all have k units in them. Okay, and lastly they say that there is a scalar output, means one dimensional output. Okay, so there is only one element in the output layer. Okay, so the structure is clear.
Yeah.
Okay, so let's move on. Okay, so like you can understand, for calculating this unit, output of this unit, I need means combination of all these p input x variables. Okay, okay, and so there they will have um, uh, how many uh, so so you can understand there will be for each element of the second layer, means the first hidden layer, for each element of the first hidden layer there will be p such combinations in denoting p such thetas. Okay, as you can see, ignoring the bias term, there were two such thetas. Okay, okay, so p such thetas need to be known to calculate this one term. Okay, similarly for every such term, uh, every unit of the hidden layer, first hidden layer, we need to have p more thetas. Okay, so for second unit there will be p required. Okay, like that, k terms. Okay, uh, yeah, yeah. Okay, so that means there will be kp parameters. Okay, kp such parameters. Okay, now for the subsequent hidden layers, one thing to understand is that for calculating, suppose one first element, first unit, means the output of the first unit, so you need k parameters for that. K parameters for that. Okay, okay, for every second layer, second hidden layer unit, to calculate one unit you need k parameters, and for each you need k. Okay, so such there are k such units. Okay, so k added for k terms, so that is k square. Okay, acha acha, maybe a minus 1 is the answer actually. Yeah, I think so. Okay, so likewise, so there will be m minus 1 such terms. Yeah, so you got that right. I think I was wrong. I was the one who was wrong. M minus 1 k square, and kp sum is there. Okay, and for the last neuron we need k such combinations. Okay, what is the answer? Let's see. Okay, so answer is C. Yes, you are correct. Yes. So these questions can be solved like this. Okay, means you can understand how many combinations, how many parameters can be required. Okay, because we're finding a linear combination of all the elements of the first layer to calculate one element of second layer. Like that we're progressing. Okay, so that is the idea. Okay, good question actually, quite commonly asked. So any doubt in this?
No, sir.
No doubt. Anybody else in doubt? All clear?
No, sir.
Okay. Okay, so let's move on. Okay, and we need to understand the different types of activation here. Okay, so what I downloaded in the when I started was the notes I had used for my class. Okay, means the class I attended. Okay, so uh, don't know how clear the scan is. It's not done very well, but no problem. Let me explain. So, the problem freezing up. Okay, so the problem starts with the means activation. As you know, we use sigmoid here. That is quite commonly used. Okay, okay. So, so this is the shape. Okay, and at less than as means the z becomes negative, it quickly falls to zero. As z is positive, it quickly rises to 1. Okay, so that is the feature we wanted as well. Means 1 is one class, 0 is another class. Okay, so works well for us. Okay, but one problem you should see here is that uh, as you remember the gradient descent algorithm here, as we are updating the parameters, suppose uh, parameter vector is theta here, maybe scalar, whatever you want to interpret it as. So what we do here is that we use a learning rate e here. Okay, and okay, so you we use a cost function. Okay, cost function, loss function, whatever it is. Okay, means for any problem we very commonly use gradient descent. Okay, acha, in the previous class, I had told to solve the linear regression problem with gradient descent or normal equation. Anybody has done that? But you must implement. Even if you have not done, you should do it, because without implementation you cannot learn machine learning. Means what is your skill of the use of this theory that you have learned? It is useless if you don't implement that. Okay, because it is all about implementation. If you cannot solve at the end of the day linear regression problem after learning linear regression, what's the use of this course? There are no such problems in the exam in the assignments, but solving MCQs, how can you learn machine learning? It is impossible. Being very good, getting 99% in this is still useless. Okay, so you must implement. Okay, I've given this Kaggle problem previously. Don't know if someone has done. So let me use Google. Not use. Okay, so yes, so as you see the example we had taken as well, just lightly you'll go over this. Okay, you should do it. Okay, in any algorithm you learn, you should try to implement. So there is the data here. Okay, and as you can see, price of house, area of house, like that. Okay, so like the problem we have seen. So these are the different dimensions of x, okay, and we need to predict the price of the house, okay. So a very common problem here, okay. So try to do it, okay, with gradient descent algorithm as well as normal equation, okay. Okay, this is the problem. Let me share. So without this, how will you learn? At least you need to implement linear regression, logistic regression, neural network, okay, back propagation, those things. Otherwise, it will not be clear actually. So, as I was telling, okay, so as we calculate this gradient here, okay, so, mm, okay, let's see. Oh, it is so okay. So we use the cross entropy or that Bernoulli distribution form loss function here, ln gz, okay, plus 1 y equal to 0 ln 1 minus uh, ln 1 minus gz, right? This is the one. Okay. So this is the cross entropy loss function. So this is the loss function in our case used for neural networks very commonly, or logistic regression or any problem. Linear regression, this will be squared error loss function, okay. So as you can see, this term, the log of gz, and gz is this, okay, and z here is the linear combination of theta and x values, okay. So as you can see from the structure, as z increases, this almost flattens, okay. So the derivative here, this gradient, okay, at higher value of z is like does not change at all, okay. So what it means is that like the gradients does not change, so we cannot update theta here, okay. We cannot update theta here. The thetas have like means stalled, they are not progressing. We're not able to update thetas to a convergence. So so this is called the vanishing gradient problem, okay. Okay, vanishing gradient problem. So the idea is that means like, so we come up with another activation function called ReLU. Okay, so the idea is like this for uh, ReLU z, suppose. So this is equals to z for z greater than equals to 0, 0, z less than 0. Okay, So this is the ReLU, what you call activation on non-linearity. Okay. So you see that at any value the derivative will be 1, okay, for positive ones, okay, and for negative one it is 0, okay. But to even aid this problem we have like a very small negative gradient, um, a slope, okay, means we have introduced to combat this problem that it does not become 0 in this case as well. So this is called leaky ReLU in this case, and it is like a very small gradient, okay, alpha z, okay. So alpha is a very small value here, okay, usually quite small, maybe 0 0.1, 0 0.01, okay, like that. And so what we do, we use that to, so that our derivatives are always positive and it's quite large, means like not too small, okay. So this is the idea of the activation. There are many other activation as well, but many of them suffer from the similar problems. ReLU is the one which, so in this when it is not 0 but alpha z, when alpha is very small, it is called leaky ReLU. Okay. Okay. So the next thing is that you have done ReLU sigmoid. There are tan hyperbolic, okay, which is taken as the activation function. There's the structure. So very similar structure to sigmoid, just that it is from -1 to 1. Okay. So tan hyperbolic, but similar, a similar problem as you see, vanishing gradient. Okay. So still there is use of sigmoid and tan hyperbolic. In the situation that we use it.
Sir, excuse me, sir. Excuse me, sir. Sir, tan hyperbolic function
Okay.
range is -1 to 1.
Yes.
If I will apply tan h, again tan hx, two times tan hyperbolic.
Okay.
So, what is the derivative of tan hyperbolic range? It will be -1 to 1 same or any other range, like as in question
It will
number
not
5.
be. It will not be -1 to 1. Range will not be -1 to 1. This problem you're talking about, right? It will
Uh,
not be -1 to 1. The range will not be -1 to 1. Okay, because you see, let me explain a little bit. Not very important, basic things actually. Range and range and domain, but let me explain. So, tan hyperbolic is uh, the from uh, domain is from let me see, just a minute. Domain is minus pi to pi, is it? Uh, okay, let me see. So take the case of tan, okay? But the range is not important, okay? But let me see. So tan produces minus infinity to infinity as range, okay? And the input is from minus pi to pi or 0 to pi, 2 pi, whatever you say, okay? Uh, okay, maybe I'm wrong or not. Maybe. Is it minus pi to pi? Okay. So when inverse, we are taking all values from minus infinity to infinity, and it should be minus pi to pi. Yes, sir. I did a mistake, I think. Let me verify from Google search. Minus 1 to 1. So what mistake am I doing? Acha, 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 acha. Forgot the basic things actually. Yes, maybe someone has answered. Because anything I'm not understand. So did you join late, Chika? Uh, but actually this are you having problem with this tan hyperbolic one or what problem? You can unmute as well. Take time to write. Means tan hyperbolic one is not important. Okay. Uh, so the thing here is that what I'm doing wrong is when we the inverse of tan is only defined in minus pi by 2 to pi by 2, not from minus pi to pi. Okay. Okay. Other than that, it is not defined. Okay. Beyond this range, it is not defined. Okay. So the domain is minus pi by 2 to pi by 2, and the range, okay, of tan. Okay, when you're trying to inverse. Okay. Uh, okay. So what happens is that uh, who I'm correct here. Tan pi by 4 is. Okay, tan pi by 4 is 1, right? Let me see what mistake I have done here. It is actually domain. Actually, domain is not minus pi to pi.
The range for tan hyperbolic is from -1 to +1, sir.
Yes, yes, it is that, but
Sir, I know range for tan hyperbolic is -1 to 1. But if we will find the derivative of tan hyperbolic, then what will be the range? If we will find out the derivative as shown in
derivative
the
of tan
question.
hyperbolic.
Yeah, yeah, yeah.
So tan hyperbolic, this is the expression. Okay. Acha, derivative gonna calculate.
I want to calculate the derivative of tan hyperbolic.
So that is
Suppose
the
the sir, suppose range of sigmoid function is 0 to 1,
hmm,
right?
okay. Yes.
So if I will find the
Acha,
derivative
range
of
problem is there.
sigmoid,
Okay. 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 Understood. Understood. Okay. Okay. So this is the problem, right? So tan hyperbolic is e to the power x minus e to the power minus x by e to the power x e to the power minus x. Right. So, so what we're going to do is you are going to take derivative, right? Okay. And the range of the derivative we're asking to find. Okay. So let's see what happens. Okay. So this range is from and okay, let's see. Okay. So what we're trying to find is the derivative, right? So what I'm going to do is multiply it both by e to the power x, e to the power 2x power 2x plus 1. Okay. Next, plus 1 minus 1 becomes 1 upon e to the power 2x plus 1. Acha, no. Okay, new slide. 1 minus, okay, 1 by e to the power 2x plus 1. Okay, and so taking the derivative here, okay, what will I get? Minus will remain 1 upon 2x plus 1 square e to the power 2x, okay, and 2. Okay, this is the derivative, and this is always negative, as you can see. Okay, yes. So here x values range from minus infinity to infinity. Okay, no problem there. And we need to find the range, right? Okay, so what I'm going to do is, it is always negative. The value at 0 is minus 2, 1, minus 2. Okay, value at infinity, limit x tends to infinity. What is it? Let's see. So it is going to be like minus 2 t upon t plus 1, t tends to infinity. Okay, okay. So what is going to be here? Acha, you can write it like, means like t tends to 0, it will also means like limits calculation. How much can I explain? Okay, so this is it. Okay, means like just invert. Okay, and so what I mean is, I have e to the power 2x, I have taken as suppose p, and what I have done is t is equals to 1 by p. Okay, and now so t tends to 0, this will be the expression. Okay, so what you get here is, what will be the limit here? Limit does not exist. Okay, or you can say that it will go towards the infinity. Okay, let me explain. Okay, just better way. So for, so first of all, L'Hopital here. Okay, L hospital 2 t plus 1. Okay, now t is once h and once minus h. Okay, okay, whatever. Acha, it will work out actually. Acha, it will work out. Oh, what did I say? So what is it working out to? So this is 1 by 2, negative. Acha. Okay, negative was also there, minus 1. Limit works out to be minus 1 at infinity. Okay, So it converges to this here. Okay, at t and minus infinity, what will be? So you can find like that, okay, and see what the range is. And it is very in simple in this case that it is always going to be negative, okay. So this option does not work, okay, as at infinity it converges to minus 1 actually. That's what I was getting, if I'm not wrong, if I've done not wrong. Minus 1 I was getting. Yes, minus 1 is the answer. Limited extends to infinity. Okay, so these two options both are wrong here. Okay, hope
Sir,
understood.
which one answer you are saying wrong?
Both are wrong here. These two. And
Which C
hyperbolic
and D?
C and D both are wrong. Okay, maybe
Sir, how you?
do these calculations again. Okay, and uh, see if it is the same. Okay, means like I got at 0, I got minus 2. Okay, so this is always means one point is negative, then you can say that it has to be, means this option is not correct, right? Like that. You can do the calculations. Maybe I have done mistake. Okay, and see derivative and limits concept. Okay, 11 12 things. Okay, see what works out here. You got the idea here. You got the idea how to do it. Okay, limits and derivatives. I can't see as I've done as well. How much you've understood, I don't know.
Question number six. I have calculated the value of P. Sir, in question number six,
6.
I have calculated the value of P by using the PMF 1 minus P power x minus 1 P. So I have calculated the value of P, and we have given the four samples, six samples, 2 to 4, 6. And from this distribution, find the MLE of P using the estimate. Find the probability of sampling x is greater than 5. What does mean x is greater than 5? What it is saying?
Greater
What is
than
the
or
meaning
equal
of?
to 5. What does it mean? 5 or 6? X is 5 or 6. Okay, do it. Okay.
Sir, can you solve one similar kind of a question? Question number
One
6.
sec.
Uh, was not the focus
Yes,
today.
please explain some kind of problem like six.
6, you want to me to explain. Uh, thing is that uh, was not
Sir, take up one
clear.
example and explain, please.
Example is what? Means like this is a distribution here. Okay. You have already calculated the value of P here. MLE of P. Just put the value of P and and
Sir,
uh,
the value of P is 2 by 9. I have calculated.
okay. So put the value of P and then put the value of X. Means like what they have given is the maximum likelihood, the probability of occurrence of P. Acha, they you you have to use the value. Acha, and and this is the probability, right? Acha, so this will be like probability. The PMF, you understand? PMF is the probability that uh, that sample X occurs. Okay. So for suppose for 5, okay, the occurrence of 5 will be given by 1 minus 2 by 9 to the power 4. Okay. To the power 4 multiplied P, that is 2 by 9. Okay. Okay. Like that for 5, for 6 you do it. Let me explain. So you got the value of 2 by 9, right? So what we're going to do now is that PMF, I think you have not studied. That's the problem. I said that you have to revise, to learn from the NPTEL NPTEL probability course that I told. Otherwise, we have problems everywhere. Okay, this course, okay, to understand these things. Okay, standard distributions. You'll get the answer here, week 4. Okay, but let me explain. So the difference between PDF and PMF, maybe you don't know that. So the idea is that uh, so PMF represents the probability at x equals to something. Okay, probability of occurrence of x uh, at the given x. Okay, like that. So they've given the geometric distributions here. 1 minus p to the power x minus 1 p. Okay. So as we put the value of 2 by 9, so what we'll get here is uh, 7 by 9 to the power x is equal to 5, so 4 and multiply 2 by 9. Okay. This is the probability. Similarly, for x equals to 6, we can calculate and add these two together. Okay. Get the value of, to get the answer. Okay. Nothing extraordinary. For x greater than equals to 5, the probability means like x can be 5 or 6. Okay, so in the case of or, you have to add this. Okay, add the two numbers.
Sir, after getting the value, calculating the value 1 minus p x minus 1 t for the value of x is 5,
Hmm.
and again we have to calculate for the value of x equals to 6,
Yes.
add up both, and after that we have to take the average or
No,
not?
just add. Add is the answer.
Acha, acha, acha.
Okay. Okay. Basic probability here. Idea. Here, basic calculus here. Limits and derivatives. Okay. Okay.
Sir, please explain question number 3.
It, yes. Yes. It is a good question for you that to I need to progress to back propagation. Otherwise, you will not understand. Okay. Maybe you should not interrupt me now. Otherwise, not possible. Okay. So ReLU done and tan hyperbolic done and okay sigmoid done. Forward propagation. Acha acha. Okay. Okay. Let's move to forward propagation. Okay. So the forward propagation. This is the structure we are using. Okay. Means that is a good question. Okay. This question number 3 is a very good question actually. And the top question. Okay. You need to do a lot of understanding to do this one. Don't rush me into this. Solve this one. Solve this one. You need to understand back propagation. Okay. It is going to take time. Okay. So the idea is gradient forward propagation first. Okay. So this is our input x here. Okay. So what they are doing is that so they have vectorized the theta that I was talking about the parameters. Okay. So what I mean by that is theta 1 1 0 like that. Theta like that means like three parameters were there. So like that. They vectorized into vector theta 1 here. Okay. And multiplied it to a1 that is x input out. Okay. To calculate z2. Applied the activation g here. Okay. Okay. Then Okay, they are also different means taking the bias term away from this and adding it steps, but you may not do it by take the bias term as x as well. That becomes a lot easier. Okay, and so you can see this. Okay, and the last is the A4 is the our hypothesis, the prediction for y, the final output. Okay, okay. So any doubt in this slide? You have to be quick. You have to understand that question. Back propagation. You have to be quick. Any doubt in this one? Is not very tough. Okay, done many times. Multiplied with the parameters. This is the theta 1, A1 is the linear combination, G is the activation non-linearity applied, and to get the output of the second layer. Okay, like that. Like that, we have to move on. Any doubt in this? No doubt? Okay, let's move. So, okay, back propagation, right? Let me show you then. There's a lot there actually. Able to cover. Can you explain again, sir? Forward propagation? So, where forward propagation is this? Just you can unmute and ask me actually. What's the doubt? It is actually simple enough actually. As you see, the x is the input we have that I have written as a1. Okay, and it has different thetas. Okay, so theta 1 from, and it is like written like 2 1. Okay, 2 1. No, no, no. So this is 2 means the notation thing, whatever means. So let me write it down. And 1 0. Okay, theta 2 1 1, theta 2 1 2. So was there two variables and one bias term? So this is the vector transpose of that. Okay, so means the vertical one is the theta 1, the vector. Okay, to calculate z2 here. Okay, then you applied the non-linearity and you have the output of this node, first node output here. Okay, any doubt on this? Should be able to understand. MLE problems we have already seen. They are not important, but if you miss out on back propagation,
Sir, this is totally different from question number three. In question number three, it is
no,
saying
it is
that
not
two
different.
layer.
Just keep silent. Okay, it is forward propagation. Okay, we need to go to backward propagation to come to question number three. It's impossible to explain without understanding backward propagation. Okay, we need to understand the forward propagation part first. Questions are very same. If you understand it properly, questions are very easy actually.
Sir, please explain once again forward propagation.
Not possible now. Otherwise, I will not be able to cover. So, backward propagation. Back. Acha, can I do it now? Okay, just see this one. That they have written in the uh, in between. Means in the bottom. Z31. Okay, is equals to the theta of layer 3. They have written 3 or 2. So their notation is a little different. So what this means is like I'm calculating for this the z value, and this is the as you can see, this pink one is the parameter this, red one is the parameter this, blue one is the parameter this. Okay, so you have to take every combination of the variables and the corresponding parameters to get the value of z1, then apply non-linearity to get the output of this neuron, A31. Okay, this is the idea. I cannot explain it once again. Okay, backpropagation is hard, cannot be. You may not understand. Let's see what can I do. Okay, so uh, maybe I can skip this one or maybe not. Let's see how much can I do. Uh, this one is visible. Not very accurate, I know. You can see something here.
Yes, sir, it's visible.
Okay. So in this network, there are R layers. Okay, R neurons at the output. Okay, so I'm getting output y1 to yr cap. Okay, cap is the output news cap output.
What theory is this, sir?
Just listen. Okay, means the last output means last layer's output I'm looking at. Okay, so the for every neuron k or the last layer, if it is 0 or 1, then it is the uh, maybe I can skip this. Okay, just what can I teach here? These are important, but maybe not time. Okay, so just look at this first one. Okay, so this is the cross entropy
What
loss.
theory is
Huh?
sir, what theory visible? Whoa. The letter, I'm not able to see the letter.
Not able to see. What can I do? Just you have to look at this loss function. Okay, okay, loss function you're able to see. So negative log likelihood
Yes,
of
sir, it's visible. Visible, sir. Clear.
yes, yes.
Your screen is visible.
Okay, let me speak. Okay, just stay silent now. Maybe I can mute everybody. See, take forever. Okay, okay, just don't talk. I'll ask to say, then you'll unmute. Okay. So this is the cross entropy loss function or of the Bernoulli form. Okay. As you can see, we have previously used the GZ as the hypothesis, so they have used the YK cap here. Okay. So this is our loss function we use in neural networks usually for classification problem. Okay. Many types of other problems also dealt with, but that is not important now. Lack of time. Okay. Acha. So first is that the loss. Let me write it down. Okay. So backpropagation algorithm. Okay. So the first is the loss in the last layer, lost or error, whatever you say. Del J theta. It is represented as Z. Suppose I write that Z0 is the last layer. Okay. Means the zero, I represent the last layer as 0. Okay. Just for the time being. Okay. So that is Z0. Okay. And and uh, okay, so this is Z0, is the vector of all the z values. Suppose there are several neurons. Okay, so z0 1, z0 2. These are scalars. Okay, so but I represent it as a vector. Okay, so this is the loss at the output, means the mismatch or error that we have, and it is equals to hypothesis, that is in our case that we are writing now. Okay, is y cap minus y is the loss, as you can understand very easily as well. The prediction minus what actually is the loss. Okay, so that is equals to derivative with respect to the linear combination for the last layer. Okay, that is a fact, as you can remember, as you can remember like that. And as you see, the derivation of that is given. Okay, del of j theta, and with respect to acha, for one input at a time. Okay, one means like they have not taken the scalar form actually, means like this is k, means the kth neuron here at the last layer. Okay, so so we have to take the derivative of the cross and entropy loss function here. J theta is the loss function. Okay, so the derivation of this equation I am showing you. Okay, so what we get is that as you can see, I'm taking this yk is 0 or 1. You cannot take derivative of that. Okay, this is a constant here, yk, and divided by yk cap, log of something derivative 1 by that. Okay, and derivative of yk cap divided by, means derivative of yk cap with respect to zk0, and like that here. Okay, and the derivative of the sigmoid function is given as, okay, uh, derivative of the sigmoid function gz, sigmoid loss is there, derivative of that will be gz. If you take the derivative, you can see that derivative of sigmoid function results in this. Sigmoid function gz results in gz into 1 minus gz. If we take the derivative, you'll see that. So that is what I have done. Okay, put the value of the derivative as yk cap multiplied 1 minus yk cap. Simplifying, and you get the expression as I told. Okay, hypothesis means negative of. Okay, I have written it like yk cap minus yk. Okay, so like that. Skipping this part, it's already late. Okay, back propagation here. Okay, so you understood the loss at the output layer, everyone? Otherwise, cannot progress. Loss at the output layer.
So how do you find a del is there, sir?
Huh?
Or the outmost? How do you
Derivative,
find a del is there?
derivative of what?
How do you find that? At out,
Hello? Derivative of what?
sir, you are telling y minus y bar minus y divided by something.
Means I cannot show everything. Okay. Derivative of sigmoid function is the sigmoid function multiplied 1 minus sigmoid function. Take the derivative yourself, you'll find that. Okay.
Yes, this one.
Yes.
Where you got this value? Y bar minus y.
Oh,
How you are
this
substituting value?
that is what I was explaining here. You have not understood? What can I do? You see, that is the derivation for that.
I think at the time you scroll fastly. I didn't see.
This is the one. Okay, I am stable now. The derivative of the, take the derivative of the cross entropy loss function. Okay, you will get the value with respect to one neurons z k0. Okay, you'll get the value this. Okay, that is what I have shown in the slide. But this is the loss at the output layer. Okay, given by the derivative with respect to zk0. Okay, anybody able to understand? Not able to understand? Somebody able to understand? Nobody able to understand? Okay.
Sir, I think this notes is available in the NPTEL, sir.
Hmm?
In your books,
What?
so your notes is available. The
Yes.
handwritten notes.
I will make it available. I will share the notes.
Okay.
But if you are not able to understand now, or how will you understand later? Whatever. Okay, what can I do? Okay. So the another part we get to here is this. Okay. As you can understand, for backpropagation, means what is the idea of backpropagation? First, let's give the intuition. Backpropagation is a very hard concept. Okay. Cannot take it lightly. Ask me solving MCQs, getting worried about that. MLE, MAP problem. Okay. Backpropagation is very important and hard to understand as well. Okay, so what I was saying is that okay, yes. So this you have understood, I hope. And gradient descent what I have written. Okay, so this is the gradient descent algorithm as you see. So for to calculate the weight means like you have to understand that we when we are means we need to train a neural network. What does we mean? We mean that we need to find the all the weights that are in the neural network. Okay, and for each of them we need to use this algorithm, that is gradient descent, to calculate the different weights. For every theta we have to use this algorithm. Theta at a future point is equal to theta at present point minus some learning rate e, usually 0.01 type, multiplied derivative of loss function with respect to theta, that the same theta. Okay, this theta. So the thing is that the the cross entropy loss function that we have here, okay, it is not directly dependent on some inner layer theta. Okay, it is directly dependent with the outer layer thetas but not with the inner layer thetas. Okay, so that is where the idea of the back propagation comes. Okay, so back propagation is we we use chain rule of derivative to to uh, to calculate this derivative for any theta del j theta theta. Okay, for this calculation of this gradient we need to use back propagation. Okay, so that is the intuition of back propagation. Okay, anybody understood? Somebody able to understand? Anybody? What do you got to answer? Prashant, able to understand? No? No answers. How will you understand that problem then? Anybody has solved this problem? Question number 3.
Sir, 1 and 2, A and B. For question number 3, A and B is the correct because
A is not
uh,
correct. A is not.
sir, del Y upon del H is depend upon WA.
Solution
Sir, how it,
I've done here actually. You can understand here. Here it's not very good quality. So what I've done is that Excel is the last output. Okay. So Excel is this y prediction of y. Okay. And sigma is the non-linearity. Okay. ZL is the last linear combination. Okay. From second last layer to last layer, I'm moving with WB weights. Okay. Like this is the chart of the calendar. Forward propagation. Okay. So what I have done is what I have written before. Okay. Del J theta with respect to ZL is equals to. Can you mute Vishwan? Mute your video. It is no. So this is XL minus Y. Okay. Hypothesis minus the original Y. Okay. And now for with respect to WB, that is okay. As you see here. Okay. Let me write it down. Okay. So like XL or what I have written here. Uh, yes. So XL is equals to here WB into ZL. This is the one. Yes. No, no, no. XL is equals to this is the non-linearity G of ZL. Okay. And ZL is equals to the forward propagation equations. Okay. ZL is equals to WB multiplied X L minus 1. Okay. See if you can understand this. This whole expression is prediction of that I've written as XL. Okay. And before applying the non-linearity sigma, this I have written as ZL. Okay. This is ZL. Okay. ZL is the linear combination of this sigma X this type. Okay. Into WB. That is what I have written here. Okay. So this ZL is the H. Okay. H, right? ZL is H. No, ZL is not H. Hmm. ZL minus 1 is H, I think. Let me see. XL minus 1. Acha, acha, हाँ. XL minus 1 is the H here, okay? As you can see, XL minus 1 I've written as the prediction this, okay? Okay. So, somebody understanding? Prashant, Arijit, Harapriya Kaur, Arun Kumar Pandey. Hello.
Yes, sir, getting your point, but I think you told that del Hy depend on WA is wrong.
Okay.
I think
Okay. Okay. Let me show you that. So del H is XL minus 1. Okay. So XL minus 1. Okay. This is H. So it is dependent on WB and only WB and this. Okay. So what is the answer here? Okay. The first one will not be. Okay. It is dependent on WB, not WA. Okay. As you can see here. Backpropagation is not easy. Somebody understanding something, then I can progress. Otherwise, I will stop here. No one is going to answer.
could
Sir,
you
answer is
discuss?
B and D.
Huh?
Answer is B and D.
B and D. So you have understood backpropagation.
And can you check that? Actually, I'm thinking answer is B and D, but
It is like
as
one of
you
guesswork is going to work actually. Okay.
because
Okay. Let me see. So WA. Let me see. So it is dependent on WB. Yes, that is correct. Okay. B and D. Right. D.
not sure, sir. B I'm sure, but D I'm having some doubt. Can you tell that D option D is correct or not? That
With
one.
respect to B. Let's see.
Yes.
With respect to B. No, it is not dependent on anything. Actually. It is not dependent on WB. WA. It is not dependent on WA. Okay, this is the expression. If you don't understand backpropagation, no amount of guesswork is going to work. To understand all this maths here, no shortcuts.
Sir, please explain about the parameter estimation techniques.
What will do
Sir,
about that?
D is not correct there.
No, incorrect.
Why? Can you explain?
So, what we have understood, backpropagation understood. Why is this dependent? You have understood. Why is del J with respect to is XL minus with respect to ZL is XL minus Y. Why is that?
Based upon that WB, right now.
Based upon this derivation. Okay,
Yes.
you have understood this derivation.
Yes, sir.
Okay, very nice. Derivative with respect to ZK0 cosine rho. Okay, that is how I've got this one. Okay, then this one. Okay, calculation of WB is actually easy enough. Let me show you. This WB I have got uh, WB. Yeah, WB I have got from here. Okay, this is the relation of ZL XL minus 1 and WB. Okay, so yeah, what I need here is that you can see when I need derivative with respect to WB. So I've used chain rule here. I have taken derivative with respect to ZL. Okay, as you can see here, ZL. Okay, and so I need to take derivative of ZL with respect to WB. Okay, that is a chain rule. Okay, so ZL I've kept like that. Okay, which I already know here. Okay, and I have put the value of this derivative. Okay, as XL minus 1. Okay, as you can see, derivative of ZL with respect to WB is XL minus 1. Okay, Harapriya, you have understood this one? It's easy enough to
Yes, sir.
understand. Not
Yes,
very
yes,
hard.
yes, sir.
Not very
Got it.
hard actually. Okay, from that relation, I've got the value of this. Okay, this derivative. And this del ZL del J theta with respect to ZL, I already know from here. Okay, so I know this one. It is not dependent on WA. Okay, these are the one which get more complicated here. Later values here. So del ZL minus 1, as you can see this one. Okay, so what I've done is like similar. It is also chain rule, but multi-dimensional here. Okay, I have explained it here. The generalized chain rule. When you want to take the derivative of y with respect to x, when y is scalar here, okay, and x is a vector of n magnitude in n dimension, z is of q dimension. Okay, so the derivative of y with respect to x is written as like this. Okay, derivative with respect to z. Okay, which is going to be q cross 1 vector and transpose of del z. This is Jacobian. Okay, called as Jacobian. Not easy, I know. What can I do? So Jacobian is like this. Okay, that is the for every z value I take derivative with respect to all values of x. Okay, so it becomes matrix. Okay, of dimension what is going to be n cross q. This matrix dimension is n cross q. So I take transpose, it becomes no. Matrix dimension is q cross n. Okay, when I take transpose, it's going to become n cross q. Okay, multiplication derivative is n cross 1 vector. Okay, so that is how I've got this one. Okay, that del j with respect to zl minus 1 is with respect to xl minus 1 multiplied Jacobian of xl minus 1 by zl minus 1 transpose. Okay, okay, so this one is, you can see.
Sir, can you share these notes?
I will share. XL minus 1, ZL minus 1, the relation is the sigmoid. Okay, just taking the derivative of sigmoid will result in XL minus 1 multiplied 1 minus XL minus 1. And this one I have used from before. This del J theta with respect to WB is this one. No. What I have done here? WB transpose XL minus 1. Cha. From where I've got this one? Acha, I've got this from here actually, bottom still. Okay, bottom I have actually done similarly, Jacobian using. Okay, I've just put it here. Okay, to calculate these values. Another thing they require is the WA here. Okay, so that will be multiplied by XL minus 2 to get this one. So it is dependent on WB. This is the thing. How much you understood, I don't know. Okay, we are stopping here.
Sir, a little. Could you discuss a little bit idea about parameter estimation technique?
Not today actually, just I found it. Okay, it's very basic. Okay,
Sir, can you share that notes here?
yes, acha, here. Okay, let me try. How can I do it here? Link. I need to prepare link, right? Okay. So Google Drive file open. Actually, I cannot. Not here. Start your mic, please. Where is it gone? Scanner. Maybe this is the one. No. I will share. Find it in the notes. Okay. Okay.
Okay, sir. Okay, sir.
Okay. Thank you, everyone.
Thank you, sir.
Thank you.